All right, so this is going to be a video all about a linear approximation problem, namely this one right here. It's multifaceted, so I felt like it was a good idea to make a video about this here. All right, so it says let f be a twice differentiable function. That means the second derivative exists with f of 0 to be equal to 4. The derivative of f is given by this function right here, and it's for this interval. Okay, part A, it says use the line tangent to the graph of f at x equals 0. So we need to figure out what is the equation of a tangent line at x equals 0. Okay, and then we are going to use that and plug in 0.25 in order to basically get an approximation of this f of 0.25. So that's what we're looking for. Okay, so first thing I'm gonna do is do this equation of a tangent line. First thing is we need to use it at x equals 0. So I need to find the slope. So I'm going to put 0 in for the derivative here, and you end up with sine of 1, which you're gonna wanna throw that in your calculator because this is a calculator problem, and you get 0.84147098848. Okay. And this should technically be an approximation because it keeps going, the decimal places keep going. So we're just gonna stop there because that's where the calculator stops. Okay, so now our linear approximation equation is going to be, I'm gonna say this is equal to the slope of that linear approximation. So it's gonna be equal to m sub L of x plus b, and you need to figure out the b, and we're in luck because f of 0 is equal to 4, so that means b is equal to 4. So your linear approximation equation should be as follows: L of x is equal to the m sub L. Now I just don't feel like rewriting this, that's why I kind of encapsulated it into this variable right here. Totally legal to do that, plus 4. Okay, now from here, we need to figure out what L of 0.25 is because that's gonna be our approximation for the f of 0.25. So what I'm gonna do is plug in 0.25 here, and you're gonna get m sub L times 0.25 plus 4. Okay, and then once you do that, you end up with 4.210 if you round to 3 decimal places, and that ends up being our answer. So that represents what f of 0.25 would approximate to if you use the linear approximation. Part B, it says on the interval from 0 to 0.25, the derivative is greater than 0. Okay, so that means f is increasing, and f is concave down because it says that the second derivative is negative. And then it says, is the approximation found in part A an overestimate or an underestimate for f of 0.25? Give a reason for your answer. Okay. So what I'm gonna do here is I'm gonna write down everything that it says, only it says the first derivative is positive, okay, and the second derivative is negative. So if we translated this, this would mean that f is increasing and that f is concave down. So both of these things are true on the interval from 0 to 0.25 inclusive. Okay, so what I'm gonna do is I'm actually gonna graph this just to kind of get an idea of what this f is gonna look like. Okay, we have something like this. All right, so this is gonna be 0.25. This is gonna be 0 here. F of 0 is 4, so when I graph what f is gonna look like, I'm gonna plot that point right there. And it should be increasing and concave down, all right? Because the second derivative is negative, it's concave down. So we're gonna be increasing and bending down at the same time. So it's just gonna be going up and bending, so it'll look something like this. And you only need this for illustrative purposes. You don't actually really have to worry about too much of the exactness of this graph, because technically speaking, we don't actually know. But what I'm gonna do is I'm gonna graph this linear approximation, this L of x right here, at this point. So it should look something like this because it's the tangent line at 0. So it's gonna look something like this. This over a little bit, so it's gonna look something like this. Okay, and we get something like that for the f. So this is f, and this is our L of x right here. Okay, and it's saying at 0.25 is the approximation, is L of x, is it going to be an overestimate or an underestimate? Well, you can see that the L of x is higher than the F of x. Okay, so you can say that L of x is an overestimate because F is concave down. If this was concave up, it would be an underestimate. You can kind of imagine that. So that's a linear approximation example problem. If you have any questions about anything in this video, let me know.